Good day everyone. Hi, welcome to the numerical and finite element method class. In this topic, we will introduce some of the basic concepts on which the direct stiffness method is founded. Today, the linear spring is introduced first because it provides a simple, yet generally instructive tool to illustrate the basic concepts. We will begin with a general definition of the stiffness matrix, and then consider the derivation of the stiffness matrix for a linear elastic spring element. Next, I will illustrate how to assemble the total stiffness matrix for a structure comprising an assemblage of spring elements by using elementary concepts of equilibrium and compatibility. We then show how the total stiffness matrix for an assemblage can be obtained by superimposing the stiffness matrices of the individual elements in a direct manner. The term direct stiffness method evolved in reference to this technique. Finally, example of analyzing stiffness method using spring stiffness will be presented. At the end of the session, students should be able to 1. Develop the finite element equations for a system of springs using stiffness displacement method CO1, PO2, and 2. Solve problem regarding spring element by using stiffness displacement method CO1, PO2. Okay students, familiarity with the stiffness matrix is essential to understand the stiffness method. First, we define the stiffness matrix by referring to figure 2-1. For an element, a stiffness matrix K bar is a matrix such that F bar equals K bar multiply with D bar, where K bar relates local coordinate X bar, Y bar, Z bar, in which nodal displacements is D bar, to local forces F bar of a single element. For a continuous medium, or structure comprising a series of elements, a stiffness matrix K relates to global coordinate X, Y and Z. Using the direct equilibrium approach, we will now derive the stiffness matrix for a one-dimensional linear spring. That is, a spring that obeys Hooke's law and resists forces only in the direction of the spring. Consider the linear spring element shown in figure 2-2. Reference points 1 and 2 are located at the ends of the element. These reference points are called the nodes of the spring element. The local nodal forces are F1x and F2x for the spring element associated with the local axis x. The local axis acts in the direction of the spring so that we can directly measure displacements and forces along the spring. The local nodal displacements are D1x and D2x for the spring element. These nodal displacements are called the degrees of freedom at each node. Positive directions for the forces and displacements at each node are taken in the positive x direction as shown from node 1 to node 2 in the figure. The symbol K is called the spring constant or stiffness of the spring. We now want to develop a relationship between nodal forces and nodal displacements for a spring element. This relationship will be the stiffness matrix. Therefore, we want to relate the nodal force matrix to the nodal displacement matrix as shown in the screen. Equation 2.2.1, where the element stiffness coefficients Kij of the K matrix in equation 2.2.1 are to be determined. Okay students, there are 8 general steps to solve the stiffness method. Step 1 now involves only selecting the element type. Consider the linear spring element, which can be an element in a system of springs, is subjected to resulting nodal tensile forces T, which may result from the action of adjacent springs. Directed along the spring axial direction, X, as shown in figure 2-3, so as to be in equilibrium. The local x-axis is directed from node 1 to node 2. We represent the spring by labeling nodes at each end and by labeling the element number. The original distance between nodes before deformation is denoted by L. The material property, spring constant, of the element is K. OK, student, Once we have selected the element, the next step is to select a displacement function. We must choose in advance the mathematical function to represent the deformed shape of the spring element under loading. Because it is difficult, if not impossible at times, to obtain a closed form or exact solution, we assume a solution shape or distribution of displacement within the element by using an appropriate mathematical function. The most common functions used are polynomials. Because the spring element resists axial loading only, with the local degrees of freedom, for the element being displacements, d1x, and d2x along the x direction, we choose a displacement function, u, to represent the axial displacement throughout the element. Here, a linear displacement variation along the x-axis of the spring is assumed as shown in Figure 2-4b, because a linear function with specified endpoints has a unique path. Therefore, u equals to 1 plus a 2x, in equation 2.2.2, is listed. In general, the total number of coefficients, a, is equal to the total number of degrees of freedom associated with the element. In matrix form, equation 2.2.2 becomes as shown in equation 2.2.3. We now want to express u as a function of the nodal displacements d1x and d2x, as this will allow us to apply the physical boundary conditions on nodal displacements directly. We achieve this by evaluating u at each node and solving for a1 and a2 from equation 2.2.2, as can be seen in equation 2.2.4. At L equals 0, a function of u is equivalent to d1x, which is equivalent to 1. When L is equal to L, d2x is then now equivalent to 2L plus d1x, as shown in equation 2.2.5. Solving equation 2.2.5 for a2, yield the equation 2.2.6. Upon substituting equations 2.2.4 and 2.2.6 into equation 2.2.2, we have u as seen in equation 2.2.7. Expression in equation 2.2.7 will now be expressed in matrix form, as shown in equation 2.2.8, or equation 2.2.9. n1 and n2, in equation 2.10 are called the shape functions. This is because the i's express the shape of the assumed displacement function over the domain of the element, when the I number of element degree of freedom has unit value, and all other degrees of freedom are 0. In this case, n1 and n2 are linear functions that have the properties that n1 equal to 1 at node 1 and n1 is equal to 0 at node 2, whereas n2 is equal to 1 at node 2 and n2 is equal to 0 at node 1. See Figure 2-4c and d for plots of these shape functions over the domain of the spring element. Also, n1 and n2 for any axial coordinate along the bar. In addition, the i's are often called interpolation functions because we are interpolating to find the value of a function between given nodal values. The interpolation function may be different from the actual function except at the endpoints or nodes, where the interpolation function and actual function must be equal to specified nodal values. The next step is to define the strain/displacement and stress/strain relationships. The tensile forces, T, produce a total elongation, deformation, D, of the spring. The typical total elongation of the spring is shown in Figure 2-5. Here d1x is a negative value, because the direction of displacement is opposite the positive x direction, whereas d2x is a positive value. The deformation of the spring is then represented by equation 2.2.11. From equation 2.2.11, we observe that the total deformation is the difference of the nodal displacements in the x direction. For a spring element, we can relate the force in the spring directly to the deformation. Therefore, the strain-displacement relationship is not necessary here. The stress-strain relationship can be expressed in terms of the force-deformation relationship. Now, using EC 2.2.11 in EC 2.2.12, we finally will obtain equation 2.2.13. Okay students, the next step is the derivation of the element stiffness matrix and equations. We now derive the spring element stiffness matrix. By the sign convention for nodal forces and equilibrium, we then have equation 2.2.14. Using equations 2.2.13 and 2.2.14, we then obtain equation 2.2.15. Then, rewriting equations 2.2.15, we obtain equation 2.2.16. Now, we later expressing equation 2.2.16 in a single matrix equation. The matrix form yields as shown in equation 2.2.17. From our basic definition of a stiffness matrix and application of equations 2.2.1 to equation 2.2.17, we then obtain equation 2.2.18 as the stiffness matrix for a linear spring element. Here, K is called the local stiffness matrix for the element. Okay, now, we move on to the step 5. In step 5, we then need to assemble the element equations to obtain the global or total equations and introduce boundary conditions. For your information, this step applies for structures composed of more than one element, such that given an equation 2.2.19, where K and F are now element stiffness and force matrices expressed in a global reference frame. In step 6, we now need to solve for the unknown degrees of freedom or generalized displacements. The displacements are then determined by imposing boundary conditions, such as support conditions. And finally, solving a system of equations, F equals to KD, simultaneously. Finally, in step 7 and step 8, the element forces are determined by back substitution, applied to each element, into equations similar to equation 2.2.16. Once the displacements are found, the forces in each element may be calculated from equation given in the red box. Okay class, previously, you have been explained on the general idea on stiffness method, specifically, spring element. Now, in this video, we will learn on how to analyze the spring elements, using stiffness method. Okay students, let's get started. In this example, we choose to answer the final exam question taken from January 2013, question 3b. For the spring assemblage with arbitrarily numbered nodes shown in figure in the screen, students are required to sketch a simple finite element models indicating the nodes and elements. Number 2. Solve for the unconstrained displacements in each element. Number 3. Calculate the internal forces in all the elements. Given that the stiffness and force values are K equals to 10 Newton per millimeter square and F3x equals to 500 Newton. Students, here are the tips in solving a stiffness analysis method. As you can read in the slide, in general, there are 6 general steps that can be followed. In solving the stiffness equation, take care of homogeneous boundary conditions by deleting the appropriate rows and columns from the global stiffness matrix, and solving the reduced set of equations for the unknown nodal displacements. Both displacements and forces cannot be known at the same node. If the displacement at a node is known, the reaction force at that node is unknown, and vice versa. Okay, now, let's answer question number 1. Sketch a simple finite element models, indicating the nodes and elements. The free body diagram of the spring is drawn as you can see in the screen. Next, we need to label all the nodes to obtain the node element connectivity, which will link local and global displacements. The labels are as you can see in the screen. Okay, we have completed answer question number 1. Now, let's continue to answer question number 2. In question number 2, the question requires us to solve unconstrained displacement. To do so, first we need to write down the stiffness matrix of each local elements. Next, we use local elements to obtain forces in each element. The general stiffness equation can be seen in the red box. F is equal to matrix K multiply with displacement D. A free body diagram of spring element 1 is shown in figure 1a. The spring is subjected to tensile forces, in which forces F1x is in negative directions, while F2x in the positive x direction. Also, in node 1, F1x is equal to the reaction force F1x. A free body diagram of node 1 shows the results in figure 1b. The full stiffness matrix equation for element 1 is written as can be seen in the red box. Similar steps should be taken for element 2 and element 3. Similar with element 1. For element 2, start with, draw the free body diagram for element 2, and write the equilibrium forces for node 2 and node 3. Repeat the similar calculation in element 1, carried out the step 2 until step 5. Finally, substitute the stiffness value in matrix form shown in step 5. Will yields element matrix in step 6. Okay students, in element 3. Similar with previous elements, start with, draw the free body diagram for element 3, and write the equilibrium forces for node 3 and node 4. Next, carried out the step 2 until step 5. Finally, substitute the stiffness value in matrix form shown in step 5. Will yields element matrix in step 6. Next, in step 3, assemble the element stiffness matrices to form the global stiffness matrix for the entire structure using the node element connectivity table. In step 4, students are required to incorporate appropriate boundary conditions. As there is a 500 Newton forces applied at node 3, therefore, F3x must be replaced with 500 Newton. Meanwhile, there is no force applied on node 2, thus F2x is equal to 0. For the displacement, d, d1x is equal to 0. This is because there will be no translational movement of node 1, as the support is fixed. Similar goes to d4x. As the support is fixed, therefore, d4x is equal to 0. Once the appropriate boundary condition has been applied, the next step is to solve the resulting set of reduced equations for the unknown displacements. In this case, d2x and d3x are the two unknowns that must be solved. Use the matrix formulation equation, hence yield d2x and d3x equal to 16.66 mm and 33.33 mm respectively. Thus, we have obtained the solution for question number 2. Okay class, for the third question, substituted the displacement into the matrix formulation. And using the matrix formulation, we finally calculate the nodal forces for element 2 and element 3 respectively. Okay students, let's have a break for 5 minutes. In this video, there are 3 exercises have been prepared for all of you. The objective of the exercises are to help all of you in enhancing your understanding to this topic. Alright class, before you start to answer the exercise questions prepared for you, you are first required to redo the example 1, which has been explained in this video. Any question regarding with the example will be discussed during the online class session. The first exercise question is taken from Final Exam Question June 2013. Students are given 30 minutes to answer the question. The second exercise question is taken from Final Exam Question December 2014. Students are given 30 minutes to answer the question. The third exercise question is taken from Final Exam Question June 2016. Students are given 30 minutes to answer the question. And the last exercise question is taken from Final Exam Question August 2015. Students are given 30 minutes to answer the question. Students must answer all the exercise questions. And any questions related to the exercise can be asked during the face-to-face online session. Okay class. Thank you very much. See you during the online class session.